Okay, good afternoon, everyone. Thank you to step up with us. Our topic is about to tackle the dependency chaos for large language model developer in the Kubernetes environment. First, to self-introduce, we come from the DaoCloud. We are the engineer from DaoCloud, and also we are the Kubernetes contributor and CNCF contributors. I'm Peter Pan, and this is Kebe Liu, and this is Neko Zhang. All right, usually we have facing a lot of challenges across AI development to the production stage. First, we have challenge about the Python and Node.js developer dependency installation not only takes time, but also the version may shift from different environments and become inconsistent. And finally, we fall into a dependency hell. And also, we have challenge about from the data preparation. Download things always takes time, right? And tend to fail due to the network solution. And also, we need to deal with different kinds of data source. And also, we have the data governance requirement in the enterprise. We need to share things across different group teams or different namespaces. And also, we need to deal with the version control and reproducibility things. So, one typical dark moment for our AI engineer is it was working on my machine, but not here. Right? Look at those error messages. I believe some of them you are familiar with them. So it was on my machine. It was on my machine. Do you think this term familiar to you? 10 years ago, more than 10 years ago, Docker was born to address this term, right? So most of you may ask, why not using Docker image to manage all of those dependencies, all those Python dependencies? You can just do a math. We have a lot of layers from the system library to the CUDA, to the Python, to the PyTorch, to the transformer, and a lot of other libraries. So you can do the preparation and combination. Those things together, the Docker image amount will become an astronomical, huge number. So, it's not very suitable to use Docker to handle all of this. So after you doing your hard work, you have tidied all the Python dependency in your developer environment. But when we shift from the developer environment to the training and then to the inference, it's not wasting of time to reinstall all of them, but also the worst nightmare is the dependency will drift. The dependency relationship will break from here to there. So we do need a solution. One solution which we define once and consists from end to end and reusable, unattended, and will integrate with the tools like Jupyter and VS Code. So do we have a way out? So Neko and Kebe, can you share us some light?
Sure. Thanks for Peter for sharing and starting this session. And let's guide everyone to go down to the rabbit hole to understand why that happens and why this thing is a nightmare for any data scientists or developers. So the core problem is when Python meets C++, the perfect storm emerge. It's because most of the ML libraries aren't just thin Python wrappers around massive C++ and CUDA-based databases, maybe runtime or maybe scripts or algorithm implementation. Everything is about C++. Okay, let's go down deeper. This is the silent thing we will encounter. Since we're going to call the whether syscall or dynamic library, it's all about API. So if we transitioning from development to training or production, API incompatibility will occur, which we will encounter some CUDA version conflicts where one driver version matches another mismatched pod version. And since then, since we need to call GCC or CMake to build our CUDA scripts, system library conflicts emerges too. And this is where we call the package inconsistencies. The real-world impact is since any of those problems may occur at any time, hours of wasting to install the CUDA environments will waste a lot of our time. Maybe we will encounter different of inconsistent model results, training results, running results, and broke the production deployments. And I would call this a hidden iceberg. And why that's a hidden one? It's because PIP can see. Why? When we're installing torch or transformers or accelerator, it's not we are only install the PyTorch itself. Instead, we will need to install GCC, CMake, CUDA, everything relates to CUDA and machine learning. That's something that PIP can do. That PIP can only manage to handle Python dependency well, but cannot determine which C++ library need to be installed or points to, and which will introduce the compiler compatibility inconsistent. So again, recall to the previous slide, the modern ML libraries aren't just Python wrappers around C++ code bases. And this isn't the only thing we need to face. The CUDA control is another nightmare. So if we're going to say we need to run a pod in CUDA node or CUDA worker node, there's two CUDA versions we need to consider. One is the driver version, one is runtime version. And for most of the current trending or widely used PyTorch versions, it will depend on either 12 or 11.8, but for 11.6, there's still some devices that depend on it, and it will cause mismatch issues where CUDA cannot be compiled or shader comes with errors. And this is another silent killer too. Often fails with cryptic errors and worse. You can't get notified before running it, or either in development or in production. Yeah, so this is because the compiler is introducing another chaos, where GCC versions with another war. Because I have introduced that PyTorch and GCC may depend on each other to build the CPython or CUDA dependencies. Since then, if we got mismatched error, those errors will occur, and perhaps some of you have seen this, like when installing transformer engine, this kind of error will appear. And that's because some of the times may occur by the mismatch version between GCC and targeted GCC. So why reusable environments matter? Like Peter has introduced, the traditional workflow got many things. Different setup across teams, hours of reinstalling, notebook or production, they are different. Or works locally and it works on my machine only. Okay, but what if we can imagine a possible future where reusable environments may be useful? Like, what if we can have one environment definition but used everywhere? What if we can install once or compile once but use for any VRM or Olema environments? Maybe it's identical for all the team members. Maybe the prod to dev to prod process can be seamlessly deployed. Yeah, perhaps we can imagine we can reduce the 4 to 6 hours of time cost to less than 30 seconds. Is that possible? It's probably possible. Since we're discovering that our solution to this, we discovered more tools and trying to experiment it. For example, if we are going to face the PIP issue, what if we can find a better PIP? That's where Envy comes in. But Envy is just another advanced PIP implementation where it cannot be aware of CUDA dependencies or be aware of C++ libraries. It cannot run or install CMake itself. So the problem's still there. But what about Docker? Since everyone is sitting here, I assume that everyone is knowing the Dockerfile so well. But why can't Docker work? I will explain that later, but in summary, it's reproducible, but the massive image size is huge. And in order to run, like, imagine we have multiple VRM or the training jobs running across over different nodes, we have to distribute each of those machine learning images into dedicated nodes. And the build time is pretty much slow, and when you are tweaking those dependencies versions, it's very hard to get the result. So it's resource intensive. But another interesting approach is Nix. And Nix is pretty new to both of the cloud native community or Linux community. While it's 100% completely reproducible, and some of I have heard that Google is already using Nix for their production. But the learning curvature is way too high, which requires a PhD level knowledge to learn it. You have to learn a complete new language called Nix in order to write those dependencies. It's very complex, and since for NixOS specifically, you have to install from the kernel to the major or core dependencies from scratch, and that's not very compatible to our nowadays container-based development environment, right? So what we need a Python package management. We need to be able to wear C++ and CUDA. We need to reduce the sizes and spin it faster and make it Kubernetes native. And more, we can share it across different teams. Here's datasets, or dataset we call it in our code base. We introduced another harmony between Python, C++ into Kubernetes, where Python, Conda, Docker, or like Containerd, NVIDIA, they will both to be able to work together. You can rule them all now. For a deep down looking, I will hand this to Kebe later, but this is a brief preview of our CRD we've already running in production for already 8 years. And for Python environment, the only thing you need to specify is which package manager are you using. We support PIP, we support Conda, we support Mamba, all of those works. And you can specify which Python version you are going to use. And just like how Conda works, you can specify the channels, specify which Conda version you are going to use, and it can also auto-install those PIP dependencies. But that's not just managing those Python dependencies. We still be able to manage Hugging Face, model scope, like downloading models or downloading data source for training later. It's very self-contained. So to deep dive into this how and this work, before that, I will answer partially for why we choose dataset instead of Docker. For Docker approach, when you trying to manipulate the base image or either the dependency, either transformers or the dataset dependency, you have to rebuild it from scratch. And for some reason, part of the NVIDIA dependencies like transformer engine requires recompiling each time. That's not easy to modify, but with dataset CRD approach, you can do incremental installation. The only thing you need to do is to specify the PVC just like we already familiar with. You can have on-the-fly build in seconds, and writable PVC can be shared across of different namespaces. To introduce this even further, let me hand over to Kebe.
Okay. Let's take a look at how the CRD works once it be created. Firstly, dataset is a traditional Kubernetes controller architecture software. First, we look at this. We will pass and validate the data spec. And then we will do some check like credential checks. Then we will check the type of the source and handle any credential security. Next, we will create a PVC to storing the dependency libraries or files. We are we are compatible with almost all the CSIs in Kubernetes ecosystem. Then we will create a job to set up your Conda environment and installing the dependencies. Once it's done, your dataset is ready to mount to any pod. The build is this handle once. After that, everyone just mount the PVC to your pod and to use your environment directly. Okay, Vance just introduced the CID structure. Here is the data spec. It's very simple and easy to understand. We can say that the environment configurations in the options, it defined like Python version and Conda's environment .yaml config and pipe requirements.txt file. This is very typical declarative approach to environment definition, but now I want to highlight something really important. We support multiple package manager, just like Conda, pipe, push, or if you prefer, use Mamba, which is 10 times faster than traditional Conda. The key is flexibility. We use whatever one works best for your workflow. We handle complexity behind the themes. Make sure everything plays nicely together. Now, let's talk about our intelligent dependency approach. Build this environment can be heavily. Firstly, we download all the sources packages with SHA verification and mirror feedback. Secondly, we build and compile the libraries and files. This is huge because completion is more time because where the compile time is spend more time. Certainly, we can auto create the metadata file, environment configurations, dependency, reduce results. This allows you to use the environment, create the dataset directly. When you open your notebook, without having executed any commands. The environment is ready to use. It's a wonderful experience. Local time difference traditional CUDA setup takes about 45 to 30 minutes. PyTorch or Lava takes 20 to 30 minutes with 30 minutes. With our solution, first setup is 10 to 15 minutes, and after that, just seconds to sign up a complete machine learning environment. That's a powerful intelligent dependency approach. But the dataset is just not about Python environment. It's also about models and data. Here's an example of looking a model from Hugging Face. Look at this. We just load a Chain 32B model directly from Hugging Face. But here's you get smart. See those filtering options. You can exclude some files and check out those advanced features if you need to regional mirror because the Hugging Face is slow in your region. Just change the endpoint. This means you can have your model ready and waiting, right? No more downloading gadgets every time you start inference. So how many sources do we support? Well, let me show you. First, I just introduced we have support Hugging Face and model scope for friends in China. Whatever your team is using, we are get you covered. Then the environment, the dependency, just like I said, the conda and the PC pipe. And for storage, we also support Git repository or S3 compatible storage or some no covalence on Premier deployments. It's through one unified API. You don't need to learn different tools for different sources. Just define your data set and we'll handle the rest. It's like having a universal translator for all your lists. Now, let me show you why data sharing is important. I can say a scenario. The team A want to download the Llama 3, set up their PyTorch environment with CUDA. It's taken about 160 gigabits of storage. The team needs the same model, same environment, boom, another 160 gigabit storage. Same model, same environment, but stored twice. Now, imagine you have 10 teams doing this. It's well taken 1.6 terabytes for the same model. It's insane. But with dataset sharing, we store it once and everyone just reference it. One model and one storage. Everyone benefits. This is how we turn chaos into collaboration. Here's how teams actually use a shared data set. It's beautiful, simple. Okay, let's look at the simple. The MLP team just create a reference data set, say the reference type, and they will point the data set in ML platform namespace. Our controller will automatically create a PVC for them. And look at the naturally it fits into your existing workflow. You just mount like a normal PVC. Your training pods don't even know what they are using or share the data set. It's completely transparent. The benefits are huge. Zero download time because the data is already here. 90% storage reduction across your organization, and you still maintain namespace isolation for security. It's the best both worlds. So what does all this sharing and catching give us? An enterprise model is in minutes. Look at this. You are get all your model organized, version controlled, with metadata automatically extracted. No more which version of Llama 3 are we using conversations. And the time serving, incredible. We used to take hours setting up environment, download models, configuring CUDA. Now we just taken 30 seconds. Just mount and go. Just mount and go. This is 95% time reduction. That transform how teams work. Instead of isolation silos with every team maintains their own model room, you get a unified ecosystem and the teams can discover, share, and build on each. This is how we accelerate AI development across your entire organization. Okay, let's back to Franz to introduce the remaining slides.
Thanks for Kebe for introducing the deep down rabbit hole for implementation and how it works. And let's imagine way beyond. We've already achieved like 30 seconds or minutes of conda installing or member installing. What if we can push these limits way further? This is where I would like to share that we may want to integrate PC directly for next evolution. So for conda, let me say, when we are dealing with conda or member dependencies, we need to waste like hours to install. Even with conda and members multi-thread concurrency, it's still taking a lot of time. But conda, the original author of the team, they decided to create a new thing called PC. The PC website is called pc.sh. It's very simple, and the grammar or CLI really looks the exact same or simpler rather than or by comparing to conda, and it will be ready in seconds. The average time it calls will shrink way better from minutes or hours back to 4 to 5 minutes. It's insane. How fast? By comparing to the original conda or member implementation, we got like 45 minutes yearly, or even precisely to say it's 100 times slower than PC implementation. So that's just another little share about this, and let's summarize it. We can boost up our time cost to like 10 times faster, and we can save the storage by 90%. We can reduce the time cost we need to load and re-downloading and sharing those datasets by 75%. That's our kind of the approximate data we measured in our production environment. And yeah, it's obviously we open source it. You can scan this QR code to get the open source repo. Try it. We would like to invite you to join us and build this together. Yeah. Okay, let me go back to the final one. And this slide is powered by front-end technology called slide diff. For any of the time you would like to interactively see this animation in your phone or on desktop, you can scan this QR code for reference. Yeah, and query time, for any questions. Okay, I guess that's all for today. Thank you for everyone coming.